All right, so I'm gonna try this again. Welcome to episode 3 of the Tattoo Sadhu Soil Tech videos. I'm gonna be working off of a script today, so bear with me. I've got a lot to cover. Um, After these, hopefully starting next week, I'm just gonna be doing shorts on Instagram and putting the full videos over on YouTube. So hopefully I can clean up Instagram a little bit and drive some more folks over to check out the YouTube channel. So we're going to take a deeper look into how ion exchange works in soils. Last time we talked about how ions get in and out of solution. And so we just want to take a closer look at some of the more important exchange factors that lead to our cation exchange capacity. We'll also look at organic matter and root exchange, but we're primarily going to look at ion exchange on clay minerals. So ion exchange in soils is reversible, as we discussed. All these actions are very dynamic and complex, but we're going to speak on them as though they are simple actions occurring in a vacuum. Remember, it's not, and we want to keep this holistic vantage point with respect to how we see fertility management. Ions are atomic structures that are charge dependent in the soil. Cations are positively charged and attached to negatively charged sites, while anions are negatively charged ions and attached positively to charged mineral sites, clay sites. And we say that they are adsorbed with a D, not a B, meaning that they're attached to the mineral surface, occupying an exchange site. So they can adsorb to a clay colloid, organic matter, or roots. CEC is much greater than anion exchange capacity, so we focus on CEC over AEC when managing for fertility. And CEC is one of the most important soil chemical properties, and this exchange between clay and soil solution is really important to understand. And if you want to do a deeper dive on this and do some reading, or if these concepts are new to you, I highly recommend Michael Estera's book, The Ideal Soil, Volume 2.0. That's great if these are new concepts for you. So CEC, cation exchange capacity, influences both our nutrient availability and our retention. So a cool thing about being an organic grower is that we lose less fertility for rain events and that sort of stuff, because a lot of our fertility is held on exchange sites or in the body and tissue of biological biology, bacteria, fungi, protozoa, all those things in our soil that are working for us. Soil CEC is the total quantity of negatively charged attachment sites or surface charges, and that could be from organic matter, roots, and clay mineral surfaces, the edges for the most part, for positively charged ions to attract ions from solution. So we talked about how they move back and forth. We want to be able to hold them on those clay minerals until the concentration in the solution of a particular ion is dropped enough that it can be resupplied off of that clay mineral site. We talked about this total charge, or we talk about this as a total charge rather than a mass quantity when we're discussing CEC. And so this includes permanent charges that are created at inception of the parent material, and pH-dependent charges that can flip depending on the pH of the solution. And this throws folks off a little bit. Mellow equivalence can be a little confusing for folks, but if you think of it as a total of charge versus an actual mass, hopefully that helps. Anion exchange capacity is the total number of positively charged sites. Anion exchange is not, as we've mentioned, as impactful as CEC, but that can change. So anion exchange is more influential and more important in highly weathered soils like we find in my home, East Tennessee or South Carolina. So it should be pretty plain to everybody that CEC is simply the ability or the potential for a soil or a substrate to hold cations in the exchangeable form that can go into solution and then be available for our plants. And so CEC is showing you the potential for what your soil can hold. Think of it as a battery, and it can hold this much. But you still have to apply the fertility, or the fertility has to be there. Um, the actual nutrient supply depends on this potential, as well as the actual amount of cations in solution. And so that simply means the soil has a predetermined potential and it can only hold so much. And that's important because that informs us to how we should approach our fertility management. Low CEC equals more applications at a lower frequency, and then high CEC, you could do fewer applications at a higher rate because it can hold more. So we're going to summarize CEC as a total charge as opposed to a weight or volume like we might want for an individual element that would be shown in ppm or parts per million. Parts per million is a mass indicator, simply looking at the percentage of a nutrient, dividing the mass of the element by the mass of the soil to come up with a parts per million metric. But here we're not looking at mass, we're looking at total charge, and the number of charges are equal to milliequivalents, or MECs. And this isn't as complicated as it sounds. We talked about milliequivalents a little bit last week. Units of CEC are described as MECs, or milliequivalents, expressed as milliequivalents per 100 grams of oven-dried soil. And this is an historical metric used by soil labs, but we also need to be cognizant of the fact that we do things differently here in the United States. And so we should look at the empirical, which is the U.S. metric, versus the metric, which is what the world uses for the most part. And we actually get really lucky here. This is one of those strange times when things just line up perfectly. So the scientific unit, as opposed to the U.S. empirical MECs, is centimoles per kilogram of dried soil. And so luckily for us, though, 1 MEC per 100 grams equals 1 centimole per 100 grams, so, or 100 kilograms. So there's no conversion to be made there. And I think I just said that wrong. There's 1 MEC per 100 grams equals 1 centimole per 100 grams. So there's no conversions needed there. So pretty straightforward, even though I messed it up the first time. So soil texture strongly influences CEC. We talked about that briefly. You have this composition of soil, 45% water, 45% air. Those go back and forth depending on irrigation. 50% is mineral, your sand, silt, and clay, including your mineral fertility. And then you got that really small but very impactful 5% of organic matter. I just mentioned that CEC and composition will impact your fertility management strategies. And so it's important to know what your CEC is. Different types of soils are going to have different CECs, and so sand, which doesn't hold much anything, is going to have a really low CEC of like 3 to 5, where you can get all the way up to 50 to 100 for our manufactured substrates. And so there's a really wide range, and you just want to know where you are. Important to remember that CEC is not everything. CEC, again, we're taking a holistic approach, so that should be clear. CEC is not everything. You can have a bunch of clay with really bad drainage, and even though you have a ton of really good clay and you can hold on to a lot of fertility, your plants might not do well. So keep in mind, we want to manage tilth, biology, and fertility, not just one factor at a time. We can also see that CEC is affected by the nature and quality of the clay, not just the quantity. And so different types of clays have different cation absorption abilities. Soils with a 1-to-1 clay have less CEC than clays that are 2-to-1. That's because of the different structures that they have. Some of you know that most exchange happens along the edges of these clay sheets, these minerals, and so it would stand to reason if there's more edges, CEC would go up. And with that in mind, you can see the soil with a similar clay content, but with a better clay, a 2-to-1 versus a 1-to-1, would have a better CEC than a similar composition with inferior clay. More recently glaciated, less weathered clays are superior. That's what we find in the Midwest, in our breadbasket kind of, as opposed to these weathered, relatively poor clays that we have in the Southeast, where I come from. old weathered clays lose CEC over time, and that's a process called isomorphic substitution, and we'll talk about that here in just a second. But as far as we won't go into all the different clays and their related CEC, but I do want to show you an example of how 1-to-1s and 2-to-1s differ, and hopefully that'll illustrate why you have a better CEC with a 2-to-1 as opposed to a 1-to-1. If nothing else, you'll be able to bore people at your next dinner party. So 2-to-1 clays are more recently glaciated. Mollisols and septisols, alphasols. 1-to-1s are older, more weathered, like oxasols, ultasols. Clay minerals are made up of either silica or aluminum in combination with oxygen. And so why those three? Silica makes up 28%, aluminum 8%, and oxygen 46% of the Earth's crust. So together they make up 82%. So that makes sense as to why we see the primary constituents of these clays to be silica, oxygen, and aluminum. How these layers stack up, though, gives them their designation as a 1-to-1 or a 2-to-1 and their associated CECs. And so I've got these crappy little drawings that I did, but hopefully folks can see these. And so here's what happens if you form a layer with silica and oxygen. You've got a Si plus 4, and so you form this octahedron with 4 oxygens. We won't get into the chemistry. I won't terrify anybody with the chemistry, but just a visual. And then here's what it would look like if you formed a layer with aluminum. And so aluminum's plus 3, and so you can form either with 6 or 8, so you form these octahedral levels, so a tetrahedral silicon level and an octahedral aluminum level. And so the central element here is either silicon or aluminum, and that makes a big difference. And then those can both form sheets where several silicons can line up with multiple oxygens and form a sheet, and then aluminum can do the same thing. And so that's kind of the basis for how those two different types of sheets can form. The 1-to-1 versus 2-to-1 is in how they line up in the soil. So if I have a single aluminum layer here, and then below it I've got a single silicon layer, and so it would be aluminum, silica, that would be a 1-to-1. And so you can see you've got a certain number of exchange sites. And then a 2-to-1 is actually an aluminum sandwiched with 2 silicas. And so you've got more exchange sites. And so hopefully that illustrates that difference there for folks. We mentioned isomorphic substitution and how that impacts these 1-to-1s. So, you can see that we've got on the 1-to-1s, let's say you've got a silica plus 4 here. Over time, millennia, we have something that happens called isomorphic substitution. And so over time, calcium plus 2, magnesium plus 2, iron plus 3, sodium, those can substitute for your silica or your aluminum. But aluminum here at plus 3 or silica at plus 4, if that's replaced by something with a lower charge, a magnesium or a calcium at plus 2, or break even at iron at F3, or even worse, sodium at plus 1, you're losing charge over time. So hopefully that makes sense to folks. And so that's a net reduction of permanent charge because of that. So that's not determined by our management, but by the age of the soil. So this is not stuff that you have to think about all the time, but I think that a lot of folks find it very confusing. So I just wanted to talk about it for a second. So let's change streams a little bit and talk about organic matter. This is really important for us as indoor growers with these manufactured substrates that we use. They don't have a true clay colloid, but something that can hold a lot of exchange sites is your organic matter. We said it's only 5%, but it's incredibly impactful. And so organic matter can have both positive and negative charges. The net charge is always going to be negative, so you're going to hold more cations. Organic matter is the easiest tool that we can impact to improve our CEC. So even with that small 5% total composition, it's really important. If in doubt, add compost. Organic matter is a variable charge, not a permanent charge like we find in clay minerals. And so it is pH dependent and depends on the pH of your soil. There's these very complex, large humus molecules, primarily made up of chains and rings, carbon and hydrogen atoms, and they interact with pH to form attachment sites. And so, depending on the pH of your soil, these carboxyl groups and phenyl groups can gain or lose a hydrogen ion. And I won't draw these out for you or make any pictures or anything like that, but just it's important to remember that these large humus molecules provide exchange sites. And then kind of similarly, a different subject but similar is root CEC. So we talked about mineral CEC, organic matter CEC, and then root CEC. Roots are made up of organic matter, so they can range pretty widely, but the CEC of your roots for monocots, grasses, and corns is 10 to 30. It's way better in your broadleaf, your dicots, your legumes, things like that. And so that's informational. What do you want to use for a cover crop? Would you want to use a monocot grass, or would you want to use a broadleaf clover? Well, the clover is going to have more holding capacity. It's also going to add nitrogen and other things, but as far as just CEC, obviously we would want to use a dicot, and so that's important information. We also want to talk about buffering capacity. It's a term we hear a lot. It simply means the soil's ability to resupply or maintain an ion in solution. And so we talked last week about you'll have a solution, you'll have all this ion concentration. As the plant removes those, the concentration drops, and then that opens up a space for an ion to come from your minerals, to come from your roots, to come from organic matter, and re-enter solution where it's available for your plants. So really important. Exchange properties of roots are attributed to the carboxyl groups the same as they are with the organic matter. We have different cations also, keep in mind, have different adsorption strengths, and so they kind of line up like by charge: aluminum 3, calcium 2, magnesium 2, potassium 1, and then sodium 1. And then there's some strange ones in there as well. So like aluminum has more at +3, has more of an adsorption strength than calcium at +2, but hydrogen actually sneaks in there between them, and although it's only got a charge of 1, it has a very, very small size. And so both size and charge density and charge are going to determine your adsorption strength. So it makes sense to us that a charge of 3 would be stronger than a charge of 2, and so that would want to attract more strongly. But also the size of the ion, if it's bigger, it's going to have weaker adsorption connection because it's physically farther apart from the attachment site. So think of like a magnet. So if you've got a magnet, and let's say this is your magnet, and it attaches to this steel pole very, very easily. But if you put something around it, if you put that magnet in a rubber ball, now it's going to be further away from the steel, and so it won't have the same attraction. And so think of that, these bigger molecules are going to be further away from the attraction site, and so they'll have less attraction, less adsorption strength. Mass action can kind of defeat this, though. Keep that in mind. So aluminum, something we don't want at +3. You could put a ton of lime or a ton of gypsum with a bunch of calcium, and just a numbers game. You can force that off of the clay colloid or your organic matter and out as runoff. That's why we ask people to add gypsum when they do a flush, because that calcium helps displace sodium and chloride ions, things that we don't want. So now that we know where the exchange comes from, let's kind of get to the heart of it as we wrap up. So base saturation percentage, and again, the Michael Estera ideal soil volume 2.0 would be a great place to start with that. But your base saturation percentage is the metric that we're really after here. And that's defined as the percentage of your total CEC, that's occupied by calcium, magnesium, potassium, and sodium, even though we don't want the sodium. And then there are base cations, calcium, magnesium, potassium, and sodium, that drive pH up. And there are acidic cations, aluminum, iron, hydrogen, manganese, that can drive pH down. So the charge doesn't make it acidic or basic. It makes it positive or negative, cation or anion. So keep those two definitions separate. And so the availability of calcium, magnesium, and potassium increases as the base saturation percentage increases. And that makes sense, right? There's simply more ions, so there's more available to your plant. And so as the base saturation percentage increases, so does pH, and those two are tightly related to one another. And so just to wrap it up, how do we quantify CEC? And there's two primary approaches. There's estimated CEC, and there's the ability to quantify CEC. And so estimating CEC is commonly performed in commercial labs. It's simple, fast. It's only 2 steps. You quantify the concentration of your base cations, your calcium, magnesium, potassium, and sodium. And then second, you quantify the exchangeable acidity, and the CEC is the sum of your charge of cations plus the exchange acidity. Number 2, the second path, quantifying the CEC as opposed to estimating. This is what's used in research labs, but it is acknowledged as the gold standard, and it's more accurate. And so there's some chemistry there. We're going to use ammonium acetate, add that to our soil sample to displace all the exchangeable cations. So it's going to flush all of those off, and then that will occupy all of the sites with the ammonium acetate. And then we flush that off with barium chloride, and then we use the ammonium that was pushed off by the barium chloride to measure to a specific CEC. And so while the chemistry could be confusing, hopefully that's a pretty straightforward example of what's going on. So lots to chew on, lots to rewatch on this video. Drop your questions and comments below, and then I'll go through a couple of examples in the next video of how to actually come up with these numbers, and then we'll move on to some stuff that's a little easier to chew on. So thank you so much for taking some time to watch these, and if you get any value, hit the subscribe and hit the like, and I'll see you next Wednesday for an IPM video and Thursday for a soil video.